Dear learners, in today's video, we are going to discuss Ewald Sphere and its relation to Bragg's law in context of reciprocal lattice. Before we begin, let us quickly recall the two key concepts that we will be using. The first one is the Bragg's law. This is the fundamental law of X-ray diffraction, which states that 2d sine theta equals to n lambda, where d is the interplanar spacing, theta is the angle of incidence, and lambda is the wavelength of the incident X-ray. So the diffraction will happen, we will get the diffraction pattern only if the condition, which is 2d sine theta equals to n lambda, is satisfied. The second concept that we are going to use in this video is the reciprocal lattice. This is a mathematical construction that allows us to visualize diffraction condition more easily. I have already explained this concept and the construction of reciprocal lattice in one of my earlier video. Now let us try to understand this step by step. Imagine a cubic lattice. In this lattice, we have different sets of plane with different interplanar spacing. Suppose an X-ray of wavelength lambda is incident on one such plane of interplanar distance d at an angle of incidence theta 1. If Bragg's condition is satisfied, the X-ray will be diffracted at the same angle theta 1. Similarly, consider another plane in the same lattice with the interplanar distance d2. The same X-ray will now interact with this plane at a different angle theta 2, and again diffraction may occur. The difficulty arises because the lattice contains a large number of planes and any of them could potentially satisfy Bragg's condition. Manually checking for every possible plane is tedious and nearly impossible to visualize directly. This is exactly where the reciprocal lattice becomes useful. To simplify the visualization even further, Paul Peter Ewald introduced the concept of a sphere which is known as Ewald Sphere. He supposed that all reciprocal lattice points lying on the surface of this sphere represents the Bragg diffracted beam. Let us consider our physical crystal on which the X-ray diffraction is to be performed, as shown in the cube here. An incident X-ray beam falls on the crystal. If it passes through it undeviated, this means the Bragg's condition is not satisfied. However, if the X-ray interacts with some other plane in which the Bragg's condition is fulfilled, then the beam will be diffracted just like this. Let us now, instead of visualizing the direct lattice, we replace it with the lattice points that make up the crystal. Again, we will denote the interaction point of the plane with the X-ray as A. Since we are now shifting our discussion to the reciprocal space, which is K space, we must express everything in terms of wave vector K, but before that, let me fill the space with the reciprocal lattice points. Suppose now we have an incident wave vector K. In reciprocal space, we represent this by drawing the vector from A, which is the tail of vector K, to point O, which is the head of vector K. The magnitude of this wave vector will be 2 pi by lambda, but just to simplify the dimension of a Ewald space, we exclude the factor 2 pi, and hence the length of AO becomes 1 by lambda. Now if we draw a sphere of radius 1 by lambda and center at A, we obtain the Ewald sphere. And according to Peter Ewald, all reciprocal lattice points that lies on the surface of this sphere represent diffracted beams that satisfy Bragg's condition. In other words, if the diffracted beam passes through one of these points, we will observe diffraction. So here, this point falling on the surface of a Ewald sphere, then I can say that this point is falling. So that means if the incoming X-ray diffracting towards this direction or towards this direction, we will get the diffraction pattern. Now suppose the diffracted beam intersects the sphere at point B. By joining point O with point B, this is just like shifting from one lattice point to another lattice point in the reciprocal space. This is my one lattice point and this one is the another lattice point. And the vector connecting them should be the translation vector, which we denote by vector G. Also, its magnitude should be n multiple of 1 by d, because if you remember, 1 by d was the distance from the origin to the first reciprocal lattice point, and then if we want to go to the second, we will have to multiply it with 2. That means this distance will be 2 by d, and so on. Now let us analyze the geometry. Consider the triangle AON. This is the end point. In triangle AON, which is a right angle triangle, from this we can see that sine theta, which is equals to perpendicular upon hypotenuse, gives us the value of ON to be 1 by lambda sine theta. And also you can clearly see that AB is another radius of this circle, so its length should also be 1 by lambda. So similarly, from the triangle ABN, we can get NB to be 1 by lambda sine theta. The length of OB, which is equals to ON plus NB, will come out to be 2 by lambda sine theta. Also, this OB is vector G, as already discussed. This is vector G. So OB is vector G, whose magnitude is n by d. So hence we got 2d sin theta equals to n lambda, which is our Bragg's law. So now let's derive the vector form of Bragg's law. For this, I have just taken the point O, A and B, and as in the previous figure, I denoted the vector AO to be K vector, vector OB to be G vector, and from the triangular law of vector addition, we can see that vector AB will be the resultant of vector K and vector G. Also, as AO and AB are the radius of same vector, so its magnitude should be same. That means magnitude of vector K is equal to the magnitude of vector K plus vector G. So calculating the magnitude by the triangular law of vector addition and cancelling the terms on both sides, we will get this expression, which we call as the vector form of Bragg's law.